So yeah, as she said, I'm Thomas Gebert.
I'm Nicholas Misturak.
And this is a distributed hash tables video and fun, so get excited. So who are we? Well, as she said, I'm from New York. I mostly do back-end processing stuff with Kafka, and I mostly complain, to be honest.
And as mentioned earlier, I'm Nicholas Misturak. I actually hail from Orlando. I work as a front-end web developer, have been doing that for about the last 5 years professionally. I got my start doing AngularJS, but since the past 2 years, basically all of my time has been spent doing JavaScript, React. I know some functional programming, probably a lot less than you guys. I know this conference tends to attract a lot of Haskell and Erlang developers. I have experience in none of those languages. My knowledge of functional programming basically extends on what's possible to do and what's pleasant to do in JavaScript. So just to preface the rest of this talk, we're also not experts in DHTs. We're hobbyists. We just had a lot of interest in developing this project that we're going to present to you. So we are kind of beginners in knowledge of that. This will be kind of an introductory talk on DHTs. I guarantee there's probably at least like 1 or 2 people who are really deep into this stuff, and for those people, if you see something wrong, be nice. And also let us know at the end of the talk so we can correct those slides if you see anything obviously out of place, okay? So real quick, just some background. What we wanted to build here today was a video sharing platform. Traditionally, this is kind of a difficult domain to get into. You might have noticed that kind of the big player, almost to a near monopoly, is YouTube out there. Part of the reason it's really, really difficult to compete with them is that they're this big centralized entity, and video transcoding and storage is just an incredibly expensive thing to do, especially at the scale that they're doing it. And you really can't compete with them until you operate at that scale, and that's just too expensive and requires too many resources for most startups out there. So our solution to this problem, to try and create a platform that may potentially one day get market share, is to not go with that centralized model. If you don't have a centralized model and you decide to distribute it, you basically take the cost of the platform out of the equation. The cost is now shared by all the participants in the platform. And in that way, you can gain market share without having to pay millions and millions of dollars sunk into some server farm out there somewhere to just 24/7 serve up the sort of web front end, transcode video, and then store it off into these large hard drive banks out there.
So what we've actually built is we built a simple, fairly efficient peer-to-peer video sharing platform. Every node in this is a client and a server. And for everything, every communication, whether it's local or across the world, everything's done with TCP. And this is a high level. Basically, everyone runs a program that's basically a little web server. It creates a little video directory. When they upload a video, it kicks off an FFmpeg. And if you don't know what FFmpeg is, it's basically a Swiss Army knife of video encoding stuff. It's very cool. And this will RPC over to a distributed hash table process. And then eventually it'll propagate to the cloud, as emphasized by that cloud. And so, some background on that. About 2 years ago, I built an initial version of this in Haskell, and I actually presented it as a lightning talk at Lambda Days. Being in a hackathon, the code was really, really messy. And it's also because Haskell's networking libraries, at least the ones I was using, were like very thin wrappers around C. And I really don't know what I'm doing. So as a result, it was a really big mess, and it only kind of worked. Also, kind of the way I wanted to do things was not completely compatible with the default concurrency models that Haskell provides with like STM and stuff. I wanted something a bit more reactive. So I really needed to rewrite a language with a bit better library support. So I actually decided to go with Clojure. One of the biggest impetus of that was I wanted a CSP lifted from Go, but I wanted it to be in a functional language because, I'm here. So and I also wanted to have really, really good networking libraries. And no matter how old I get, no matter how long I live, I will never have time to write Java. So So Clojure also, besides from the Go style concurrency, Clojure actually also has a really good transactional memory system. They call them refs, and for simpler versions, they call them atoms. And it's so if you need a simple lock-based concurrency without having to deal with locks, it has that covered too. And this is something that might get me beaten up after this, but I kind of feel that dynamic languages are a bit easier to work with for low-level networking stuff for a whole variety of reasons I'd be happy to talk about afterward. So some of the software and library we used, I used a library called GeroMQ, which is a port of 0MQ. It has bindings for virtually every language, but this is the Java bindings. If you get nothing else from this talk, you should look at 0MQ, especially if you're stuck using a less enlightened language while you're at work, because it gives you a lot of nice networking concurrency guarantees that you don't typically get with Java or PHP or whatever draconian language people use nowadays. We use something called message pack, which is a binary serialization thing similar to protocol buffers, if you've ever used that, but it's a lot simpler. It's kind of like JSON almost, but binary. And core async, which as mentioned is the Go style CSP for Clojure, held together with macros and praying. For the front end, we used something called Reframe, which is sort of a port / reinterpretation of React for ClojureScript. And to those who don't know ClojureScript's Clojure that compiles to JavaScript. So one thing that was giving me anxiety when I first built this was there's this whole bit of PhD theses about how to split up video, then glue them back together, and I'm not that smart, so I was really concerned about that. But it turns out that this has already been solved by web standards with HLS Streaming. So it actually literally creates a Winamp playlist, M3U8. You can request that, and it'll actually arbitrarily request the chunks on the fly and glue them together. And so the amount of work I did on that was nothing. The browsers did that for me. So I keep saying distributed hash table, DHT. What is a distributed hash table? Well, distributed hash table is a decentralized distributed data structure that gives you hash table-like key value semantics, but it has no central authority or entity. Data is shared and replicated automatically, and there's a few algorithms out there. In academia, you have stuff like Chord and Pastry, and in industry, like for example BitTorrent or a few others. There's Kademlia is probably the most popular one, or at least modified versions of it. We did Kademlia because it's one of the easier ones to implement. It's by far the most popular, at least in industry. It's used by, the word in the street is that it's used on Facebook and other companies to distribute updates, and it gives really good lookup times, even with really, really huge clusters. So the thing that, one of the things that Kademlia does is provide something called a routing table. And a routing table gives us a way to look up nodes that are interesting to us for whatever reason. And the point of it is, if the cluster were to get giant, it's infeasible to store everything, every information about every node, because if it's something as big as BitTorrent, there's billions of devices running it, and so you'd be dealing with gigs or terabytes of information on just how to get to a thing there. So what we want to be able to do is store a very small subset of all the nodes in such a way that makes it easy to find any given node. And the best of these are faster than linear time. I guess that's the rule for life. Every machine participating in the node in the DHT is called a node, and nodes are given random 160-bit IDs. And actually, in the Kademlia paper, they kind of say, ensuring random IDs is an exercise left to the reader. So, thanks, but. So I'm just using dev random, so I'm sure some security expert could explain why I'm horrible on that. But, and they have something called distance. And distance is nothing to do with geography or Euclid or anything like that. The distance is defined by taking two IDs and XORing them together. And that gives you a number back, and smaller numbers means it's closer, and bigger numbers means it's farther away. And that's, from when I first learned that seemed really dumb, but it actually is not, because A, XORing is really cheap, and B, it's a sort of a deterministic way of calculating distance that doesn't require any other knowledge of the outside world. So every single node has its own routing table. And the tables are divided into something, they call them K buckets, and for the sake of this demo, let's assume it's 5. They don't say how many to put on there, and BitTorrent has sort of dynamically sized ones. So let's assume we have this routing table of the entire address space of 0000 and 11111. And assuming that I'm the red dot in the middle there, or the left there. So this guy comes along, and he wants to, we encounter him for whatever reason, and we're thinking, should we add him to the table or not? Well, there's plenty of room, just let him. So we're happy with this, but then notice we have 5 more in there now. So what do? Because the bucket size, as I said earlier, is 5. Well, you know what we can do? We can split the bucket in half. He's on the left side, so just plop him in there. So this happens, but now we have a bunch. We have 5 on both sides. And this guy comes along, and notice he's on the right side of the address space. And we don't want him. Throw him away. But when no one comes on the left, we can put it on the left side and keep splitting the buckets. And as a rule, basically, if we can keep this splitting the buckets that we're in into smaller subdivisions, it creates this recursive tree. And as a result of this, we get every single node has a lot of knowledge about their neighbors, and if you assume that everyone is doing this, then you can fairly easily query any given neighbor from any one, as long as you have some distribution of the address space. Eviction is done fairly simply. Eviction, we want to remove dead nodes if someone turns their computer off or crashes or they decide to live in the forest and turn off their internet. You just simply ping every node you have knowledge of, and then if you get a response back, good, keep them in the routing table. If it takes too long, then you time it out, you trash it, and then you remove it. Yeah, so it's the kind of the beautiful part of this, and why Petar, who created the algorithm, got his PhD for it, was because storing the nodes this way allows us to convert this address space into this kind of simple and elegant directed graph. And you typically don't end up with cycles or anything like that. And lookups are logarithmic, and it becomes fairly cheap in a relatively small amount of hops to get to any given node that you have the idea of.
So I'm going to talk a little bit about how we actually store and retrieve information out of our DHT now that we have kind of a concept of the various nodes that populate the DHT and how to route to them. We kind of exploit this ability to be able to address these different nodes in our DHT by these 160-bit IDs to also figure out how to store files. And this is where the hashing aspect comes in. We mentioned earlier that the IDs that are assigned to the nodes are just random 160-bit strings. The way we store files is we hash the file name to also produce 160-bit IDs. This can be done in a variety of ways. The only real sort of requirements for your hashing function is that the hash that gets produced is the same length as the IDs of the various nodes within your DHT, and that it gets good distribution so that you're not saturating one particular part of your DHT. And in this way, you can sort of match files to individual nodes, or at least the closest node on a DHT. So let me just go and show you an example of how we store a file in here. Say we're the purple node in the top left of this image here, and we have a file that we want to propagate throughout our DHT. The initial step we do is we hash the file name to get a 160-bit ID from that, and then we try to match it to something in the DHT. Let's just assume for this case that the yellow node in the sort of middle to lower section of this image is the closest match. We don't have a direct route to that from this particular purple node, so instead what we're going to do is we're going to pick out of the routing table of that purple node our 3 closest neighbors, the neighbors that match closest to the file ID that we just hashed out, and push the file to them. So that looks like this, and then after this step, each of those 3 nodes will actually receive a copy of the file and store it for us. And this ends up running on a loop, like a timed loop every hour or so. You can fiddle with the settings in terms of how often you want to do replication. But essentially what ends up happening is this process is recursive, where now all of these 3 nodes that have this file, they try to find a better match. So they look in their own routing tables. They can see different nodes on the graph than our initial node could that are actually closer matches. So each of them finds 3 nearest neighbors. It could resolve to the same ones. As you can see, the top one and the second one on this list end up having some shared matches that they push the file to, or they can even push to each other. But the sort of long-standing result of this is eventually what you have is this file will move across the graph until it ultimately kind of resolves down to the closest match that it can find in the DHT, at which point there's no closer neighbors that it can find to push the file to. And in this way, you get good replication, and you have some guarantee that from any particular node in this graph, they can eventually find, by trying to just search for the closest matches of that file hash, that ID that was assigned, eventually hop to a node that has that file. So we can take a look at how that get side of it kind of works. So now imagine that we're the green node on the top right side of of this image, and again we're trying to get a file that we know. We're just going to assume in this case that it exists in that yellow node down there. So it kind of works like the storage logic, but in reverse. So in this case, we figure out what hash that we're searching for, and rather than searching for 3, we just search for the nearest one. We're not trying to replicate this file, we're just trying to get it, and it doesn't matter what node it comes from, and it doesn't make sense to search for the second closest or the third closest, so we just pick the closest. So in this case, it decides this particular node is the closest match. If it can't find the file there, it, similarly to the put logic, asks that neighbor, hey, can you put me in contact with some of your neighbors that might be a closer match? And if that's the case, it ends up causing us to route to the next closest neighbor in the DHT. And then again, this process is recursive, where we just keep trying to find closest neighbors until we either find a node that has our file, or after a certain amount of jumps, we just kind of make an assumption, it's probably not in the DHT, we should give up looking.
So for node communication, as I mentioned, we're using a TCP, using GeroMQ, and a little bit of lower level UDP stuff I'll explain in a bit. And I don't know if many people here have no closure, but the way we define this RPC is using a multi-method, which I guess in this crowd it makes sense. It's sort of like the pattern matching in Erlang for dispatching functions, but you have to define your own dispatcher. So Kadamlia in the paper, and of course you can define more, it defines, means you have to have a ping, so you can ping to see if a node's alive, store a value, get that value, and find, which is just looking up a node in particular, and not necessarily a value. Anyone here who's done network engineering can collectively groan about NATs, network address translation, because they are the worst thing made by humans. And so, yeah, they're a pain, because to those who don't know, NATs are effectively what your router has to share one IP address across lots of devices in your home network. They're useful, and I hate them, because that's sort of a code word of saying, I don't know which device to talk to. And they're really hard to work around for doing network engineering. People get paid a lot of money to figure out the best ways of dealing with it. I actually emailed the dude who made the Kadamlia algorithm, and his response here was basically, I don't know how to solve it either. So, but there is a way to solve it, and it's called hole punching. People seem to think you can only do it with UDP. It's easier with UDP, but you can do it with TCP, but I did it with UDP. But basically, since external computers don't know how to talk directly to the computers within the NATs, without them doing some sort of elaborate port forward, which I can never convince my mom to do, what you can do is you have a central server that they both can connect to, and through their router. And since now a socket's been opened up between the computers and the server knows how to stitch them together, and you can have a direct connection. But if anyone's been paying attention, we don't want a central server. That's the whole point of this. So this is an algorithm that I thought I invented, but I talked to someone who worked at Akamai, and they claimed that Akamai invented this like 20 years ago. So I reinvented it. But basically, every node that has an open port will get a priority on the routing table. So if we come along, the eviction logic, or the inserting into the routing table logic is slightly different, that a node with an open port on the router will always be willing to replace one with a closed port. And for every K bucket, we maintain a constant connection with them. And upon encountering a new node, it will constantly publish any nodes with open ports that it has reference to. And then when you try to get from a closed node, the hole punch will always be attempted and see if it's a mutually connected node exists. It doesn't always work. It just gives you a higher hit rate than if you don't do it. Something, this is probably again going to get me a beat up after this, but something you want if you wanted to really clone YouTube is you need mutable data. You can't just make a file system, because if someone's making a video series or something like that and they want to put in the description a link to the next video in the series, they need to be able to update this description. And distributed systems can be really finicky on how to figure out how to do that directly. We get around that by just using a vector clock. Vector clocks are a whole thing. I don't know if I implemented mine correctly. I think I did. But basically, vector clocks allow a partial ordering of a distributed set of data. Basically, whenever an item is modified in some way by a node, a counter on there is updated. And everyone's doing this all the time. And so when incompatible two updates happen, you have to conflict it. And for this, we cheat a little bit, and we also publish the wall clock NTP time, and we just choose the latest one after that. So only if there's a conflict. So it doesn't happen that often, but in the case that it does, we cheat.
So I'm just going to talk a little bit about some of the front-end work that went into this project that we completed here. But before I get too deep into that, just a word on JavaScript. I mentioned earlier, I'm not a Haskell programmer. I'm not an Erlang programmer. I'm not even a Clojure programmer, even though we did this project in ClojureScript. Really, this project was kind of an excuse for me to learn a little bit of ClojureScript. But I actually wanted to talk a little bit about JavaScript first. I actually like JavaScript, which I think might actually be sacrosanct at this talk. But I would contend with anyone that JavaScript actually punishes the OOP programmer. I think people kind of overlook JavaScript from the functional programming side, but that's fertile ground for pulling would-be functional programmers, because anyone who's done it long enough knows that if you don't know a little bit of functional programming, you're going to hate life and you're going to fail in every project that you work on, essentially. It's really, really good about kind of funneling you towards at least, I think, some of the more introductory material regarding functional programming. But for the people who do have criticisms of it, point taken. There's plenty to levy there. There are large gaps in the language, a lot of traps in the language as well. A lot of the standard library tends to focus around mutation-heavy kind of stuff. There's plenty of array methods that will absolutely reshuffle and reorganize the content of that array when you don't expect it, or other things that might just end up outright destroying data or mutating it in ways that you can't obviously tell from looking at the code. And if you're not familiar with the language, it's easy to get bit by that. There's also things that are really nice to have and are pretty common in what people consider pure functional programming languages that are just straight up missing out of JavaScript, and people come up with all these little hacks to kind of get around it, but it makes it unpleasant to use. So yeah, and then there's the thing that I call the pit of despair, which is anyone who touches these features is just completely screwed. There's no way to do them right. There's no way to write clean code with this. If you touch classes, prototypical inheritance, or you acknowledge the existence of null in the language, you're writing code that's going to bite you later. Promise. So why did I choose ClojureScript? There's basically kind of half the reason, I guess, is our backend is in Clojure, and I like uniformity across that. At work, for the same reason, I tend to like programming the backends in Node.js, just because I don't like switching languages too much. I guess I'm lazy in that way. But the other half of it is I actually really like ClojureScript, the language. And the reason I like it is because I look at it, and weirdly enough, I see a lot of similarities between JavaScript and ClojureScript, which seems weird. You have this one thing that has this very sort of Java-ish syntax, and this other thing, which is a Lisp that looks like something out of 50 years ago. But the reality is, there's a lot of sort of shared underpinnings there. One of the ways that they kind of share a similar design philosophy is this idea of relatively few data structures. There's not a whole lot of type worshiping that happens on the Clojure side. Instead, you basically got your 3 data types, which are vectors, sets, and maps, if I believe, and lists, excuse me. But then in JavaScript, you kind of have a similar idea of everything is either an array or an object if it's not some primitive type. But the advantage to that is there's tons of functions that work with those basic data types. So you spend very little time kind of re-implementing the wheel. Usually you can reach for something in the standard library, and it's going to work with whatever crazy composite type you created, because your crazy composite type is really just a map. Or it's really just an array, and there's already 500 functions written for those things. The other thing that I kind of liked about ClojureScript using it is it really does embrace this idea of dynamic programming, I think is how they refer to it. And that encompasses the obvious, which is it's a dynamically typed language. So you don't really have to fuss about so much with types, which again, I know in this conference is kind of sacrosanct. But the other nice thing about it is it's a language that tends to get out of your way and also encourage a more sort of interactive approach to development. Most people who do front-end web development, they spend a good chunk of their time throwing code at a REPL and getting a response back. That's a very similar sort of workflow that ClojureScript kind of brings to the table. And the last thing I'll say about ClojureScript is that I've had a lot of problems with JavaScript. Maybe not the same set that people tend to think about with JavaScript, but again, it kind of maps more towards features that would make it easier to do functional programming. There's plenty of talk of adding these features, but in a lot of cases, they're just already in ClojureScript. And some examples of that are things like what I have listed on this slide. Basically, what you're looking at is a list of proposals to the JavaScript standard that are already things that we have available in ClojureScript. So something like optional chaining, which is basically a safe navigation operator. It's a way of pulling deeply nested properties out of an object without running into null pointer exceptions. This actually, since I last gave this talk, this recently just got added into the standard, so it's finally there. I can actually probably remove this off the top of this slide. But everything else in this slide, still outstanding. Pattern matching, a pipeline operator, so a way of actually like easily composing functions together where you pipe the results of one function into the input of another and get our ability to build larger functions out. Still have to reach for Lodash and its compose, or sorry, I think it's flow, or whatever they're calling it now. I think they've changed the name of it a couple times in order to do this. Do expressions, the ability to have this expression-based kind of control flow. I still have to sort of anytime I want to turn an if statement into something that's more expression-based, I have to throw in an immediately invoked function expression just to get it out of the way. So there's a lot of things that are just a lot more straightforward and easier to do in ClojureScript. Other niceties that kind of come from ClojureScript, immutability by default. As I already mentioned, it's expression-based, so you don't have to worry about the sort of expression versus statement dichotomy in the language. Homoiconicity, so it's really pleasant that the entire program is written in data structures native to the language. The other things is it throws out the junk of programming. I'm sorry, JavaScript programming. There's only one null type in the language. There's not this crazy dichotomy of a triple equals versus a double equals, which hopefully most people in the room don't even know about. You don't want to know, I guess, is the point of that. And the last thing I'll talk about with regards to the front end, I mentioned earlier that I'm a React programmer, so I just wanted to touch a little bit about how Reframe specifically kind of addresses some of the React specific concerns I have. Basically, if you don't know, React buys you two things on the front end. It's a way of kind of pairing up your JavaScript code and your HTML code and kind of bringing HTML into the JavaScript language. The way that React does it is it actually does a non-standard extension to JavaScript. So you're technically no longer coding just JavaScript. It's now this superset language that also has a brand new primitive data type in the form, or I guess it's a composite data type in the form of JSX, which stands in as your HTML templating language. I hate it. The reason I do is it brings all the pain of HTML and that syntax into the language, but also has a bunch of things that aren't actually standard HTML to kind of escape out of some parser errors and stuff. And then you have this escapement syntax that you have to glue up on top of it to figure out, okay, am I coding JSX now or am I coding standard JavaScript now? And I find that anytime I sit down with someone who's new to React and have them start programming, they're immediately lost on that. They always trip up on that for a little bit before they start going, okay, now I'm in a JSX context or now I'm in a JS context. ClojureScript says, I'm sorry, Reframe specifically says, no, we're just going to use native data structures. You want HTML, you're going to have to basically program it as these tuple sets with symbols. And it sounds like it might be awkward at first, but it actually does a lot to simplify how you code these templates. And it makes it really easy to reason about because you're just working with the existing data structures of the language. There's nothing special about them, I guess. The other big thing that React hands to you is state management. So you have your HTML template, you have some JavaScript behavior attached to that, but then you have to manage the state that's associated with all these different components that you have in your system. The way that Reframe tends to tackle this is similar to Redux. If you haven't heard about Redux, it's a separate thing from React, but it's kind of a library that tends to be paired up pretty often with it. I like the core model of Redux, but there's a lot of pain points. Most people complain about boilerplate, and I think it's 100% a valid criticism to levy against Redux. Reframe cuts a lot of that out, so that's the big reason that it's nicer to work with. But the other half of it is Redux is like half the picture. Everything is synchronous. You can't do any sort of effects by default. The way that you have to do that is either write your own middleware or grab more libraries like Redux Saga or Redux Loop or Redux. There's like 1.5 million that are targeted to just bringing asynchronicity and effects to Redux. And in the case of Reframe, it's just built in. You can return effects to the Reframe library, and Reframe will then handle that effect for you. And in that way, it's a lot more pleasant to write.
So it's software, so nothing's ever done. And so I have plans. I sadly was not able to finish this before the talk, not for lack of effort, but I want to verify this using TLA+. I don't know if people know what that is. It's basically Leslie Lamport's thing of using set theory to specify distributed systems. You can model check and write proofs if you're ambitious. And yeah, it does a pretty good job of like testing every branch there, and it makes me feel intellectual, so I like it. And the thing I described actually has an inherent security problem, and that's called a Sybil attack. And this is true of virtually any distributed hash table by default, where someone could conceivably spin up 1 million nodes on a computer, and then occupy the entire network, and then start deleting data, and then panic ensues. This has actually been addressed by Petar, the guy who created Kadamlia, in a follow-up paper called Tonica. It's a lot harder to read than Kadamlia, so I haven't finished implementing it yet. Soon. I'd like to have unlisted videos, and that's relatively easy by just using GPG to sign them first, and then that way no one can decrypt them without a special key. And I feel like it's computer science, so I have to mention blockchain at some point. And I want to incentivize people to open up their ports and contribute CPU cycles and stuff. So my long-term goal that I'll probably never finish is to make it have some sort of reward for doing that using blockchain or something else. If someone else has other ideas, I'm very interested in hearing them. So if any of this stuff is interesting to you, it is. It's cool. I got one a bit crazy with the QR code generator, but the original paper is actually pretty easy to read for Kadamlia. It's only like 15 pages, but the last 6 are a proof. So if you just treat it as an axiom, then it's only like 9 pages. For us, we had a really good talk talking about how the routing table works. It's really good, better than mine, so you should watch that. If you want to get a hold of me, that's my information. If you want to get a hold of Nick, that's his. We have a quick demo. If you would like to see it, you're hostage. You have to see it. But so let's upload a video. And fortunately, I have so let's just call it
UI for video uploads incoming.
Yeah. Well,
TBD.
This is developer UI. You don't need anything more than that.
Postman is your UI.
So we upload this. This uploads immediately. It's a very short video. So, and you might think, why didn't I spin this up beforehand? And I just say, shut up. So no. So it's already finished the transcoding, and now we can play this video of a train. So this is actually, well, right now it's on my computer. Within the next 45 minutes, assuming I leave this on, it'll propagate to my home server, and it'll propagate to my wife's computer because she loves me, and it'll eventually propagate to the nearest computer on the node, which only has like 4 computers on it. So, but still, it's someday.
So you're like virus, you're spreading.
That was the initial name for it. But, and with that, that's it.